Hello, good morning, everyone. Yes. Okay, thank you. Well, it's really a pleasure to be here, especially because of the special nature of this workshop. I've known Ian and Matt both for very long time. I think coming close to maybe 25 years or more even. And it's great to be here to celebrate them. And thank you so much. And Ian has been so inspiring in his mathematics. We've worked together also on some projects, and it's really always such a source of insight and creativity and ideas and imagination. And so it's thank you. So the problem is there's something missing from the top of the screen here. But anyway, hopefully this will not be a problem. Okay, so I'm going to talk about physical measures, and I just want to start with very basic material that most people are familiar with, but just to set the context. So when you want to study dynamical system from a statistical or probabilistic point of view, then the fundamental object is this sequence of probability measures, right? So you start with a point X, which is an initial condition, and you simply look at the first few terms of the orbit, and you look at the Dirac deltas along the first end points of the orbit, right? And you spread these Dirac deltas on the orbit and you take the average. So each of these is a probability measure. And if you think of n being a million, for example, then you're looking at the first 1 million points along the orbit, and each point carries 1 millionth of the measure, right? So if you now look at your space from a distance and you look at this as a probability on the measure on your space, then wherever you see measure means there's a lot of points, right? So if you see there's a set of measure 1/2, then about half of those points are there, right? So this is using measure theory just simply to describe the initial part of the orbits. And this is a sequence of probability measures. It's a sequence. So as n increases, of course, you're taking longer and longer pieces of orbits. So this probability is shifting, right? This probability measure is shifting according as to where the orbit is spending a lot of time on. So the fundamental questions we ask about this is, so you have a sequence of probability measures. If this sequence converges as a sequence of measures, then clearly it means that mu is describing the asymptotic statistical behavior of x, because that means that when n is very large, this measure here is very close to the measure mu, and the larger n is, the closer you are to the measure mu, which means the measure mu is describing the distribution in terms of the proportion of points in different regions of space, right? So if you have a limit of this measure, then you have described, in some sense, in a very precise sense, the asymptotic statistics of this. However, you may also have situations where mu n does not converge, right? And this is a more curious, but also in some sense very interesting situation when you really think about what that means, right? So the non-convergence of this means that you have several limit points. So assuming that if you're in a compact space, then limit points always exist, right? So non-convergence still means there exist limit points. So you have two limit points and you have two subsequences that converge to these limit points. What does it mean that you have two subsequences? This does not mean that you're converging to some convex combination of these two, right? Because converging to a convex combination is still converging to some measure, which is the convex combination. What this means is that at different time scales, you see different statistics, right? So this means that if you look at this sequence Ni, it gives you a sequence of time scales. And if you look at this sequence, then you say, okay, I look at Ni, I look at this measure here at time Ni, and I see that it is very close to this measure. So that means that at that time, the frequency, the distribution of the points of the orbit is very close to this certain distribution. But if I look at a different time scale, then it looks like a completely different distribution. So just to give a practical example, that corresponds to if we're tossing a coin, right? We all know empirically when you toss a coin, you expect to converge in some sense to a 50%, 50-50 heads on tail distribution, right? This corresponds intuitively to the fact that this converges. But imagine that you had a situation where you were tossing a coin and the proportion of heads and tails depended on the number of times you toss. So if you toss your coin a few hundred times, you get 90% heads. If you toss it on the order of a few thousand times, you get 90% tails. If you toss it over the order of a few million times, depending on the time scale, you see different statistics. So it's a very curious behavior. And it's not something that we see very much, but we are finding more and more examples of systems that we find that exhibit this. And I will talk about some of these today. So a standard definition is that mu is a physical measure. If the basin, I don't know if you can see this law, but if there is a set of points of positive Lebesgue measure which converges to mu, right? So in other words, if you have mu n of x converging to mu, you can ask, okay, is it just that initial condition? This mu n of x depends on initial condition, or excuse me, are there many initial conditions which converge to that? If there are many initial conditions that converge to the same measure, then we say that mu is a physical measure to indicate that if you choose a point at random with respect to Lebesgue, you have positive probability of picking a point that's going to converge to that statistics. Okay, so this is just a little bit of basic philosophical background about the approach of what we are studying here. So given a dynamical system, we would like to know what happens to these statistics of the orbits, right? So in particular, if there are physical measures, if there are no physical measures, and so on. So yes, this is supposed to be x plus x, 1 plus gamma, the intermittency map. This has been extensively studied, including by many people here in the room today. And for every 1 plus L, sorry, there's a sigma. This is it. This is the map we're looking at, right? X plus X, 1 plus L. And it is a full branch interval map. It's got a neutral fixed point at 0, depending on the value of L. So when L equals 0, this is just x plus x, which is 2x mod 1. And we all know that for Lebesgue, almost every point, these statistical averages converge to Lebesgue itself, right? So Lebesgue is the physical measure, and almost every point, the statistics converges to that. For L between 0 and 1, we have that for Lebesgue, almost every point, the Dirac averages converge to a measure that is equivalent to Lebesgue. Not equal to Lebesgue. And then there's as you know, there's a seemingly dramatic break in that a very interesting thing happens when L is greater than or equal to 1, is that for Lebesgue, almost every point, the statistical averages converge to the Dirac delta at 0. Even though this map is always topologically conjugate to 2x mod 1, right? So it's a topologically mixing map. The fixed point at 0 does not become an attracting fixed point. It is still a repelling fixed point, right? But this, when you look at the derivative is given by 1 plus Lx to the L, and L essentially determines the order of tangency here. And when L is large, the tangency is more degenerate. So it's a very high order tangency here, and the fixed point is stickier. Can you see what it says here? Yes, is in some sense sticky, right? So even though all these points, they still have dense orbit in the interval, right? So the topological limit points is still the whole interval. From a statistical point of view, they spend more and more time near zero. So because they get stuck, because it's so very sticky, because when you're close to zero, it takes a long time. Even though it's repelling, it's very weakly repelling. So beyond a certain threshold, the stickiness dominates, right? And that's why you have this threshold where L equals 1. So when L is 0, 1, in some sense, it's also getting stickier, but we call it non-sticky. And then here it becomes sticky. Okay. So we're going to generalize the family of maps that I want to introduce today is a generalization of this family. And it consists of a family of interval maps, which are still full branch with 2 branches, but have 2 possibly neutral fixed points, both sides here. And then we also allow at this discontinuity to have infinite derivative or a critical point. Okay, so we embed this, the usual intermittency map in a much more general family. Let me give just the precise formulation. So this is the way we define. So we take 4 neighborhoods. This is neighborhood of -1. So we assume this is the interval -1, 1, just for the sake of setting up the notation. And then we assume that the map here in a small neighborhood of -1 has this form. In a small neighborhood of +1, it has this form. And in a small left and right neighborhoods of U0, it has this form. And what this means, if you look at this form, we've included some parameters, but it's essentially exactly the same as the usual intermittency map. You can see the derivative here is 1 plus just some constant, 1 plus x to the L1, right? So as x tends to -1, right, this tends to 0, so the f prime tends to 1. So here you have neutral fixed points, right? And exactly the same thing. And L1, again, it controls the order of the tangency of the graph here. So this is just exactly an intermittency map, but we have it on both sides. And then we, again, so here you can see that the derivative of this map is minus a constant times x to the k1 minus 1. Right? So depending on whether k1 is less than 1 or bigger than 1, this goes to infinity or 0. So if k1 is less than 1, right, then this goes to infinity, and you have this situation where the derivative is infinity. And if k1 is greater than 1, then it goes to 0, and you have a critical point, right? If k is very large, you have a very highly degenerate, arbitrarily degenerate critical point, right? With very, very critical. And so these 4 constants will play an important role in parameterizing our family of maps: L1, L2, K1, and K2, right? They give you the orders of all these various things in these 4 neighborhoods, right? So these parameters B1, B2, A1, A2, we put them there just for generality to show that you know, that that doesn't matter, actually. It turns out that they play essentially no role whatsoever, which is also somewhat surprising. But these 4 parameters are very important. Okay, so this is our first assumption. And then our second assumption is very mild. What happens outside these neighborhoods? So we assume that outside these neighborhoods, the map is C2 and is expanding, essentially. So if you have a critical point, then we don't really, it's a little bit milder, but a bit technical, and I don't want to put it. So if we have a critical point and the neighborhood is small, then we don't need to assume the derivative is necessarily bigger than 1 outside these neighborhoods, but just that even though the derivative is small, if you take a few more iterates, then the derivative will be big. So think of it as just a mild expansion condition outside these neighborhoods, but it's a very natural condition and not very strong. So this is all. This is the definition of the family. There's nothing more complicated. It's simply defined by the fact that it has this specific form inside these neighborhoods, and essentially expansion outside these neighborhoods. excuse me. So this includes a lot of, so this includes many well-studied variations of this map. And at this point, I want to plead forgiveness from anyone who I forgot to mention, because I think almost everyone in this room has worked on various intermittency maps. So I've just given a few references that are particularly relevant, but it is amazing, you know, how many, literally, I think probably 70% of people here have worked on intermittency maps. But in the particular kind of direction that we're studied of particular importance, I want to mention the papers of Liverani, Sossolo, and Vaienti map, and also the so-called Pikowski maps, which is how we actually ended up coming to this, which was studied by Alves and Araujo, and also in a paper of Cristodoro, Hayden, Marie, and Vaienti in 2010. And in fact, this, maybe I should mention that this project started with my PhD student, Mubarak, and we didn't know about this paper. We knew about this paper of Alves and Araujo, and this is a paper that has there's a map that has 2 neutral fixed points and 2 infinite derivatives, right? But it's symmetric, right? So an important feature is that it's symmetric. So Lebesgue measure is actually invariant in that case, and we wanted to generalize that and construct a induced map. And then we found your paper, and we almost abandoned the project because we thought, okay, it's done that already. And then we realized we could add critical points as well, and that opened up a new direction, which proved to be very fruitful actually and very interesting. So as I said, there's many other papers. Yes, so our first result, this is joint work. We have 2 papers that I'm going to talk about. The first one will appear in Communication Mathematical Physics, is joint with Mohammed Mubarak, who was my PhD student from Nigeria, recently graduated, and Doug Coates. And is that in all cases, with no additional assumption, you always have a sigma finite ergodic invariant measure equivalent to Lebesgue, which is kind of generalizes the usual results that are known for the usual intermittency map. Yes, I should, so the proof uses a double inducing scheme, which is a kind of a variation of what's used also in the paper of Hayden and Vaienti. And the methods are relatively standard, but there are some subtle points, which is maybe worth mentioning here. Just for example, that the fact that this, so we construct an induced map. The induced map is constructed on a one-sided neighborhood here, actually, of the discontinuity. And you need to, I will not have time to define the construction, but it does play an important role in our result. And you basically induce from one side to the other side, and then from this side to this side, and then you compose the 2 induced maps. And that way you actually get a first return induced map, which, however, contains information about what happens in all the neighborhoods that you want to have information. And one of the things, of course, you need to show is that the induced map is uniformly expanding to show that it gives Markov. And this was not obvious. We realized that we could introduce fixed critical points when we realized that it worked even with critical points. So even though you have critical point here, and even though the tangency might be very degenerate here, still, if you take a point very close to here, the derivative is very small, and then it comes very close to here, it spends a long time here, enough time to compensate for the small derivative and to become expanding, right? And this is easy to see asymptotically. It's a back of the envelope calculation asymptotically. So when you use the definition, you say, okay, if you're sufficiently close. And in some earlier version of the paper, we assumed that those neighborhoods were sufficiently small. Okay, but we removed that assumption, which is very important. Actually, it's something that is kind of behind the hood. So when I define these conditions, I'm not saying that those that the neighborhoods where the map is defined need to be sufficiently small. They just have to exist, and that's it. And this required a little quite a subtle, technical, interesting argument. And yes, and as I said, the inducing keeps track of, an important part of the inducing scheme is it keeps track of the time you spend on the left and on the right, which will play an important role afterwards. Okay, so going a little bit further into those statistical properties, the key quantities that play a role, as I said, are these four constants, L1, K2, and L2, K1. But in fact, what turns out to matter really is only these products, right? And so L1, K2 is the product of this order and this order, right? And L2, K1 is the product of these two orders. And if you think about it very just intuitively, you know, these are measuring the stickiness, right? This is if you didn't have the K1 and K2, this would just be L1 and L2, and this would be measuring the order of tangency and the stickiness of the fixed points. Now, imagine here that you are somewhere here, and you at a certain distance from the discontinuity, and you iterate once. If this order K2 is very large, so that the critical point is very degenerate, then you will come very close to zero, right? So the combination of K2 large increases the stickiness indirectly because the order doesn't change. But if you take a point close here, you will come very close, right? Whereas if you have an infinite derivative here, so if K2, okay, here, if K2 is small so that you have infinite derivative, you take a point very close, then you iterate it, and then it will immediately move much further, so it will escape much more easily from that, right? So it turns out that this is that's the way that these two exponents interact, right? By taking the product of these, that's what measures the stickiness. Turns out that that's what measures the stickiness of the points. So we're going to define a whole family and separate it into three subfamilies. And the first one, so beta is just for convenience the maximum of these two. So we define, first of all, the family F, which is where beta is 0, 1, which means that both points are 0 than 1, which in some sense is not sticky, right? Continuing the analogy with the intermittent fixed point, it's a small. In other words, both beta 1 and beta plus are small. Then we have the family where beta is greater than or equal to 1, and beta minus is different from beta plus. So in this case, when beta is greater than 1, then at least one of them is sticky, right? Not necessarily both of them, because beta is the maximum. At least one of them is sticky, possibly both, and one is stickier than the other, because necessarily one of them is bigger than the other. And then we have the case in which at least one of them is sticky, possibly both, and they have the same. Actually, in this case, they both have to be, because they're the same. So they both are greater than or equal to 1, right? And both points are equally sticky. So notice that this includes everything, right? So all the possibilities are included in this very simple classification of these maps. And we're going to study systematically. It turns out that is very nice description for each of these families. So we first of all, in this paper with Mubarak, we study F, which is the non-sticky situation. And we show that this sigma finite measure is actually finite, right? So there's a unique ergodic invariant probability measure, mu equivalent to Lebesgue. So this is the physical measure. And we study various properties. The measure mu satisfies Pessin entropy formula. This apparently was not obvious. This is a corollary of a paper of Jose Alves, actually, that allows us to apply this. We have polynomial decay of correlations with this particular rate, which are all fairly expected. And then we have various limit theorems that satisfy, that we prove in this situation, that depend on the observable, depend on the constant. So these are relatively the decay of correlation is the usual estimates on the tail of the induced map and so on. The limit theorems is not really my area of expertise. This is really Doug and Mubarak's contribution here. But I will mention them because I know there's a lot of experts in limit theorems here, and I think we get a fairly interesting situation with the limit theorems. So of course we are looking at the convergence in distribution. We have these various kinds of limit theorems depending on this scaling factor gamma n, like central limit theorem, non-standard central limit theorem if you have a slightly weaker, or stable law if you have this kind of convergence, right? And it turns out that we get a very interesting playoff between the various, okay, I don't think we're missing anything crucial up there, but yes. So there's a playoff between the values of beta and the values of the observable, right? So it turns out that we define this b theta depend on the observable, and the values of the observables at the endpoints, we get this different conditions. So we get, in some cases, central limit theorem or the non-standard or stable laws, depending on depending on this combination of factors, basically. Okay, which I think is interesting because it is a feature of this particular system that has these 2 points. So it's a kind of a fairly unusual situation that we get these combinations. Okay, so this is what we have for the finite, the case in which the 2 neutral fixed points are non-sticky, right? So now we look at the other 2 classes that I defined before, right? When at least one of these is sticky. And this is our result. So this is a more recent paper together with Douglas Coates. So in the case F plus or minus, okay, you can imagine what's happening here is that one point is stickier than the other. So the orbits are going to get tapped on the stickier points, right? And in fact, that's exactly what happens, is that for Lebesgue, almost every point, when you look at these Dirac averages, they converge either to the Dirac delta in the fixed point -1 or to the Dirac delta in the fixed point +1, depending on which fixed point is stickier, simply, right? So the picture is quite intuitive, and it is, again, similar to the usual intermittence situation. So again, remember that these maps are all topologically conjugate to 2x mod 1. So it's like in the intermittency map, these points are not attracting, it's just become it's just from a measure theoretic point of view, this is where these become the physical measures. What about when the 2 fixed points are equally sticky? What do you think? For those who do not know already, some of you know already. What's going to happen when the points cannot decide because the 2 points are equally sticky? We get stuck in the stickiness. And in fact, we don't get stuck. So what happens is that for almost every point, the sequence does not converge. I've prepared you for that. But we were surprised, actually. This was, for us, the highlight of the result of this research that we did here. And I at least really thought that there would be some possibilities where you could, for example, converge to some convex combination of the 2, right? That you could maybe fine-tune those other parameters, A and B and so on. But it turns out that this is not the case. So since for Lebesgue almost every point is not converged, then in particular F has no physical measures. So this is a class of map that has no physical measures in this case. And so we give really a very just we've taken a large class of maps, we divide it into these three subfamilies, and for each subfamily we have exactly say what the physical measure, or whether there's a physical measure and what kind it is. Notice that this accounts for all maps in our class, right? There's no unresolved boundary cases. There are actually some boundary cases in terms of the proof. When beta is equal to 1, some of the arguments need to be specific arguments, but fortunately we're able to resolve that. It's always a bit annoying when you need to leave out some of these boundary cases, but it's all exactly this. Yes, so for me it's interesting that there's no times when the physical, you just cannot get a convex combination of the two. And as far as we know, this is a new mechanism for the non-existence of physical measures. There's only very few examples out there. The most well-known one is the Bowen's eye, that many of you are familiar, which is a kind of continuous time system where you just oscillate between two fixed points. And in some sense, this is analogous because you're oscillating between the two fixed points, but of course underlying you have a topologically mixing system, which in the Bowen's eye you don't. There's also an example of Keller and Hofbauer-Keller in the quadratic map, in which also you have topologically mixing systems. I don't know how to compare their example to this one, or to know if somehow they are, the mechanism that produces the lack of physical measures is similar or not. Okay, so any questions? So here, yes, I just wanted to say maybe very, very briefly, I'm not going to really say much about the proof because it gets fairly technical, but just the most technical slide, just to focus on the fact that basically the whole argument of all the results rely on the construction of information about this induced map. So we have an induced, okay, you cannot say, but we construct the induced Gibbs-Markov map, a young tower that many of you are familiar with, and it has a return time tau that is naturally split up into the sum of two blocks, which is the time that the orbit spends on the left and the time that the orbit spends on the right, right? Or on the right and on the left. And in fact, these two blocks are consecutive, right? So the way the induced map has a very nice structure, because you start with a point and then you spend a certain number of blocks, iterates on the left, and then a certain number on the right, and then you come back. And that's it, right? And so the partition, maybe I was going to say maybe I will just quickly do, since I have a little bit of time. So if you imagine, just to give you an idea, so let's say we have this picture here. I don't know how well you can see it from there, but we have two intervals here, which we call this delta minus, and another interval here, which we call delta plus. And it's not difficult for those who are familiar with maybe the usual intermediate. Well, you can see that you can fairly easily construct an induced map from here to here, right? So if you look at the backward iterates of this, you will have these intervals that converge to that map to this, and you can pull back this to a partition here. Okay, so here you have a induced map, full branch induced map, where each element maps full branch to the other side, from delta minus to delta plus. And then you can do the same thing from delta plus to delta minus. So you take these little intervals here, and they go here, and they come back to delta minus. So you have two full branch maps, one from delta minus to delta plus, one from delta plus to delta minus, and then you can just take the composition of the two. So the composition of the two means that you're taking this here, partition of delta minus here, and then each element here. And then when you go starting from delta minus, when you look at this inducing to delta plus, you're spending all the time in the right-hand side of the interval, and then you come back, right? So so you just start here, but then you switch to the right-hand side, and then you stay on the right-hand side all this time. So if you have a certain inducing time from delta minus to delta plus, this is our tau plus. This is the time it takes to come back. And then it comes back full branch here, and here there is the corresponding partition. So this, you can pull back this partition with this induced map, and so you refine this partition with another with the time that then each of these subintervals will map to a subinterval of the partition here, which then has a certain tau minus return time, right? Okay, so I know this is very sketchy, but you have this interesting double inducing, and you have this interesting structure where for each part, so you then now have a first return map from delta minus to itself, and the structure of the partition is that you have one partition, and then you have a refinement, and depending where you are on the higher level partition, you know that that's tau plus, and then for each tau plus, you have a distribution of tau minus inside that, right? That depends on the tails here. So the estimates for the various tails that you do by taking into account these orders, and then you pull back, and so you get a kind of distribution of tau plus, and then your conditional distribution of tau minus inside tau plus. Okay, so this was maybe just for people who are familiar with similar constructions before, but I just wanted to point that out. And yes, so we have these distribution estimates for tau plus and tau minus, but the most important ingredient for us is that we define this tau tilde, which is the difference between these two, right? And what does the difference between the two mean? The difference between the two highlights if you're spending much more time on the right or much more time on the left, right? If this difference is large, both positively or negatively, that means that you're spending much more time on the left or much more time on the right, right? And this is in the second, for the final result, this turns out to be the crucial quantity, and we have some distribution estimates for these, and these are all positive observables, whereas this is a signed observable that can be both positive and negative, right? And we have these distributions for tau tilde in positive and negative time. And the most important thing we show is that this tau, if we then take the induced distribution, right? So we take the distribution when you look at an orbit, right? And you look at, so this tau tilde depends on just where one point is, because it depends on the inducing time, and then you look at its image. So you take the average induced observable, and the induced observable converges in distribution, this one here, to a random variable with full support. Okay, so basically we are showing in the end that this is going to get arbitrarily large both in positive and negative time. Okay, and this will give us the fact that we have this lim sup is positive, is plus infinity, and the lim inf is minus infinity. Okay, which exactly, yes. So this is the key point in the end, to be able to show that we do not converge, because we spend infinitely much time on one side and infinitely much time on the other side with the right frequency. Okay, this is just a very brief sketch, of course. Sorry? Perhaps. Okay. Yes. Maybe. Yes, maybe. Okay, I don't know. Tell me afterwards. Maybe you can tell me which result you're talking. Whose result? Zweimüller. Okay.
So, yeah, your generality is, has a novelty compared to that. It has a special example. So I don't
Yeah.
say.
Sure, sure, sure. No, it would be interesting to see. To be honest, I already told John afterwards because I looked at the papers of Roland and other papers, and the language, the setting is always is a language and a setting that I have difficulty always understand. Sorry. I I'm saying that I did my best to try to understand those papers, and I'll be very happy to understand. Okay. Okay, so just to finish off, I want to say that we now have these three classes. So it's a natural question: is how robust is each of these phenomena? Right? We have this F, we have this either we have a probability measure equivalent to Lebesgue, or we have Dirac delta measures, or we have no physical measures. How are these three classes put together in this family? Which one is most prevalent? Which one? So first of all, let's say how big the in some sense, we want to focus first on the non-existence of physical measures, how big this is. And so let me remind again our definition, and notice that just by trivial observation is that F star contains a 3-parameter family of maps, right? Because your only condition here is that beta 1 equals beta 2, right? Now, if you fix any beta greater than or equal to 1, and then for arbitrary TS arbitrary, you can just choose your map with these constants. L1 equals to S, K2 is this, L2, K1 is equal to this, and you get a map in F star, right? So it's in some sense you can think of it codimension 3 family inside this family, all of which. So it's a kind of persistence, right? I think this is an important feature of this map. This is not, the Bowen's eye and the Hofbauer-Keller example in the quadratic map. They're all very delicate and very unstable, right? Here, in some sense, we can argue that it's relatively robust, right? Or there's at least in two ways, it's robust in the sense that there's certainly a lot of flexibility in the parameters that still has no physical measure. Also, if you think about condition A2, so this is building on condition A1, condition A2 actually shows it's not an immediate consequence, it's slightly more sophisticated, but we have a theorem that says that if you choose a map F that has no physical measure, and if you take any other G in the family, such that if you look at the difference F minus G and you look at the support of F minus G, the closure of the support. So if you take a perturbation basically of F that is strictly contained inside the two left-hand side and right-hand side, then if it's a small enough, in fact, it does not even need to be small enough. As long as it's still in the family, then automatically this also is an F star, is no physical measure. So this is a kind of defining a class of perturbations that you can make, which guarantee that you're still without physical measure, right? It's a way of saying that this absence of physical measures is persistent in some ways. Okay, if you assume that this difference is very small, you don't even need to assume a priori that you take a map in F star. But anyway, okay, and finally, yes. So again, if you want to generalize a little bit and talk about perturbing the map in some topology, the problem with these maps is that everyone who works with these maps has found is to find the right topology on the space of these maps, because they have discontinuities, they have infinite derivative. You can't just use the CR topology. But it turns out that for our purposes, there's a very, very natural way to define a topology. It's a very natural topology, which is this. You take two maps in F, sorry, this should be F tilde, and you fix R, right? And then you can define a distance between these two maps that is the CR distance if the distance is CR and infinite otherwise. Okay, so this is sometimes called an extended metric. So there are points that are infinite distance from each other, but you can also kind of renormalize it by a standard technique. And this is a very natural metric, and we have the following result, and I want to give a kind of user warning for this result, because there tends to be some emotional reactions to this in the following sense, that at least is the one we had and other people do. So the first impression is, no, this is amazing, okay? The immediate second impression is, well, this is so amazing that it can't be true. You must be cheating. Aha, okay, of course you're cheating. The topology is cheating you. And so actually this is meaningless, this result. And I think average of all these feelings is correct in the sense that there is some limitations to this result, but I think it is still a remarkable result. And it is the following, is that, well, every F in F tilde and every epsilon, there exists three constants, three integers bigger than 1, R tilde, R plus minus, R star, that depend only on your original F, and maps F tilde in F, F plus minus and F plus, so you can find three maps in each of these classes, which are epsilon close to the original map F in this topology. Okay, so what we're saying is that we can approximate any map in any class by map in any of the other classes, right? And then we have a specific formulas in a certain topology, right? But in particular, in one, you know, in C1, it's all true. So in particular, each of the families are C1 dense. Each of these subfamilies is C1 dense in the whole family. Okay. So you can approximate a map without physical measures, C1, by a map with a measure that's equivalent to Lebesgue, probability is equivalent to Lebesgue, or by one that has Dirac delta physical measures, and vice versa in the C1. But often you can do it with much higher topologies as well. That's why I stated it in its generality, because the result, and the topology depends only on the constants K1, K2, L1, L2 of F. Basically, it's just depends on those constants in a fairly complicated way. So of course, when you start thinking about it, so the first stage is this, it looks like an amazing result. I think it is an amazing result. But then you think, okay, but how can I be approximating all these high topologies? So of course, a key point of this approximation is the fact that in the family, when you have neutral fixed points, you have the possibility of changing your constant L quite significantly while remaining close in the C1 topology, for example, right? Because independently of what L is, since the derivative is getting close to 1, all the family, you're always kind of close in the C1 topology. Okay, I'm not trying to diminish the result, but also explain that, of course, there is that. I don't think it's cheating, but it's just part of the nature of this family, that's how it is. So this relies on the fact that near the neutral fixed points, we can make relatively large changes to the parameter L1, L2, because that's what you do when you approximate here, right? So you take a map say without physical measures, right? So beta 1 and beta 2 are big, and you want to approximate it with a map which has a probability measure equivalent to Lebesgue. So you need to bring down, you need to approximate it with a map where beta minus and beta plus are less than 1, and you can do that by changing L1 and L2 quite easily, okay? So it's true that is the case, but nevertheless, this topology is a very natural topology. I think it's justified in thinking about it as a CR topology, and so this result holds as it is. It is a part that you can approximate in the CR topologies, and that's how it is. Okay, so I think this is an important addition also to the results to have studied in this family, the kind of very intermingled nature of these families. And so I think I will finish here. Thank you very much.
Questions? Yes.
Discussion of?
The whole tilde.
Yes.
What you need to do more to treat the case of beta equals to 1? I mean, because here you're treating the case of equal stiffness, but beta bigger than 1.
Yes, you don't have exactly this. You have a slight variation of this. You have a slight variation of this. Oops. It's a slightly different technical point. I think we can look at the paper together afterwards, okay, because we don't actually get this, but we get log. I think on the bottom it's a slightly different estimate here, okay, but gives the same result. Yes.
So I'm trying to understand your final theorem, and I'm just thinking, let's go back to the LSV map. Is your theorem basically saying, is it just the observation that all the LSV maps are close to each other?
Well, this is just the topology is not my choice about what's close to what.
Yeah, you're just saying in this topology, all the LSV maps are close to each other. Is that correct?
Well,
yeah, but those don't affect anything apparently.
No, change this one topology.
Oh, okay. So you allow some extra parameters in the LSV family, and then they all become, and then you can make gamma anything you like by a small perturbation. I mean, I'm just trying to. It just looks to me like that this is a proof that it's the not good measure of closeness.
Yeah, you're in the second phase of the emotional reaction.
Yeah. Right. Yes. Okay. Right.
Yes.
But it will address the synchronic behavior.
Yeah. Yeah. So it's not good. Okay.
Well, yes, I think what Mateus is saying. So this includes the distance outside the neighborhood of the neutral fixed point. But inside the neutral fixed point, if you take R small, then yes, then the maps are all close in that neighborhood. Yes.
Yeah. Okay.
Yeah, that's only to do with the asymptotic behavior, not with the actual.
So the other comment, I guess, is as you probably realize, there's this whole subject out there called infinite ergodic theory, thanks to John Aronson, and then there's other notions of physical measure that may, from some perspectives, maybe people might think that's the more interesting one, the absolutely continuous invariant measure.
Yeah.
The fact it's not a probability measure is not a good reason for not looking at it.
No, I am. I'm very interested in learning more about this.
Okay.
Yes. I as I said, I've been. Ian, John is questioning your comment about infinite physical measures.
All right. Are there any more questions, or you want to do your discussion afterwards during coffee time? Yes, you have one.
Velocity in this distribution of the function tau tilde.
Yes.
Is it essential that you have a Markov structure? So it's a first return map, or if you have not full branch Markov at very beginning. Can you
Oh,
still have something?
oh, I don't know. We do what we can with what we've got. Yes. Yes.
Great, thanks.
Sure.
And any further questions? Yes.
Lyapunov exponents.
I think that's coming up next, right?
But for this
No,
family also?
I think that's a very good question. So maybe what I should have said is that I think there's a lot of questions that come out of this, and because there's very many natural generalizations of all the work that's been done for the intermittency map. And I think this question about the Lyapunov exponent is also one. Many of these questions are questions that certainly for other people to do outside my own area of expertise. This one on the Lyapunov exponents is something that I would also be interested in thinking about, because I've not done that. And I think it's a very interesting question. For the infinite measure case, and maybe, maybe there's some suggestion. I think in the case where there's no physical measures, there's particularly a lot of interesting questions. For example, whether every measure is a limit point of the sequence, right? And I think that maybe is the case. I know that there are some situations where you can have, or every invariant measures can appear as a limit point, or I'm not sure. But also whether some people have suggested, I think, a very interesting question, which is you now have the sequence of measures that has many limit points, right? Is one of these limit points better than others, right? What is the frequency? What is the statistic? Meta statistics, right? So you have many limit points, but maybe some of these limit points are accumulated with more frequency than others, right? So they might be very interesting to see, in this case, which are the limit points that you get, and if some of them are more interesting, maybe that could be a kind of higher metaphysical measure question.
Thank you.
Yes.
All right, so let's thank our speaker once more.
Thank you.
All right, our next speaker is Yushi Nakano. He talked about existence and non-existence of Lyapunov exponents for random non-hyperbolic dynamical systems.
Maybe here. Okay, good, thank you. Wait. Can you hear me? Okay, nice. Thank you for the introduction, and thanks to the organizers for giving this opportunity to talk in such a great conference. And in fact, I really want to say happy birthday to the professors, maybe, but they're not here. But oh, yeah, they're coming. Oh, happy birthday, Professor Melbourne, and happy birthday, Professor Nico. Okay, so today I talk about the Lyapunov exponent, and it consists of two parts. One is about the non-existence of Lyapunov exponent for deterministic dynamics, especially for some non-hyperbolic system, meaning that without dominated splitting. And this is basically based on joint work with Shinkiriki, Sharon Lee, Teihiko Soma. And in the second part, I consider its random perturbation. So I consider the existence of Lyapunov exponent for such a random dynamical system. And this is based on the joint work with Fumihiko Nakamura and Hisayoshi Torukawa. Yes. So I start from the first part. So the setting is like this. So I consider some Shewan map on a compact Riemannian manifold. And I said X is Lyapunov irregular for some non-zero vector V if it's the Lyapunov exponent does not exist. And I say that point X is Lyapunov irregular if X is Lyapunov irregular for some vector, non-zero vector V. Yes, and I denote it by Li, Lyapunov irregular set, as a set of points with Lyapunov irregular property. And my question is this: is the Lyapunov irregular set is observable in the sense of the positivity of the wave measure for many dynamical systems? I should say that someone consider another definition of largeness, like a residuality of a positive dimension. And some people did work on the Lyapunov irregular set, like Paolo Barandas did nice work, but sorry, today I don't talk about it. So my question is the positivity of Lebesgue measure for this set. And I will precisely explain what I mean by many. Yes, and I want to consider this problem because for some people, positivity of Lyapunov exponent means a signal of chaos. And I think some people compute Lyapunov exponent by computer. And I conclude that, okay, this is positive, so I found the chaos. And I'm a little bit scary about the attitude. So if the answer to this question is yes, maybe this is a warning to such attitude, I guess. Okay, so I want to give a few but important remarks. Firstly, the famous oscillator multiplicative algorithmic theorem ensures that the Lyapunov irregular set is always zero measure set for any invariant probability measure. But in general, this has no information for our question because invariant measure, Lebesgue measure, it's not invariant in general. And the only known result about the question is the work by Otto and York. They consider such a surface flow. There's a saddle point, and it's homoclinically related to by homoclinic loop. And this is dissipative. Yes. Then they showed that the Lyapunov irregular set is Lebesgue positive. That means that for any point very close to this loop and the inside of this loop, and you take vector v as a flow direction, then the Lyapunov exponent oscillate between 0 and some negative value. Great. But the problem is like in the previous talk by Stefano Lusato, yeah, this is very close to the bow and eye example, and it's very easy to broken. So it's not stable under perturbation. So yeah, and there's another issue I would say is that they only consider in their method, we can consider only the vector v along the flow direction. And this special direction is, of course, not observable in the sense of the tangent space. And as proof, their proof is specific to their dynamics. I a little bit communicate with Tom York, and yeah, they said yes. So we decided to a little bit different, to take a different approach, meaning that considering the Newhouse region, in other words, dynamics with the robust homoclinic tangencies. And I say that I want to find many examples whose Lyapunov irregular set is positive. So I need to take care of this factor. So if F and G is C1 conjugate to each other, then the positivity of F is equivalent to the positivity of G. Yes, so I need to, sorry, take care of it. Okay, so our result, first result is like this. So let us consider M as a closed surface, as usual, denoted by diff Rm, the set of shear diffeomorphism on M with regularity larger than or equal to 2, and denoted by N, the Newhouse region. meaning that the set of diffeomorphism with hyperbolic set and homocline tangency associated with it. And this property is robust, meaning that you can find a small neighborhood of G, and for any element of this small neighborhood, you can also find a hyperbolic set and homocline tangency associated with it. Yes. And what we found is that some diffeomorphism in the Newhouse region, such that for any shear neighborhood O of G, there is an uncountable set L in this neighborhood, satisfying the following. So any distinct element of L are not C1 conjugate. So I'm not cheating in this sense. And for any F in this set L, we handle positive Lyapunov irregular set, meaning that there exists open set UF in M and VF in R2, occurs under the identification of tangent space with this product space. And for any X in this space, this set, and for any vector in this set, Lyapunov exponent oscillates, does not converge. Okay, and yes. Yep. It is close to Newhouse region. Yeah. Sorry, you mean this last statement, UF is invariant in what sense? Yes, and in some uncountable set. And I guess this set is in the Newhouse open set, but I cannot say yes or no. Yeah, I just saying that there is some set inside the small any small neighborhood of O. Yeah. Okay, I draw the picture. Sorry, I forgot. So you take G, you have G, and for any small O, so orbitally close to G, you can find infinitely many Lyapunov irregular example. Yes. Okay, and maybe Stefano Lodato understands Barkov irregular behavior. So maybe you guess that this is a consequence of the kind of Barkov irregular property, but it's not true. I want to emphasize it. So this is moreover, L can be decomposed into two uncountable sets, R and I. And please remember that this U was a subset of Lyapunov irregular set. So this point X is always Lyapunov irregular. But if F is a member of R, then time average exists. So I call it Barkov regular. And if F is a member of I, then the time average does not exist. So I call it Barkov irregular. So lucky things for me is that Yuririma already asked about the Lyapunov exponent, the coat example. And my guess is that the Lyapunov exponent of your example is 0, because they are staying very close to indifferent fixed point. So I guess it is 0, I guess. Okay, and Crovizier and Dawayan Junfazan constructed a three-dimensional partial hyperbolic diffeomorphism whose Lyapunov exponent always exists, but the time average does not exist for some continuous function. Yes. So their class is maybe here, and our class is here, and like a hyperbolic class is maybe here. Okay. And okay, and maybe some of you like to consider the Lyapunov exponent is the Barkov average of the projective dynamics induced from the original dynamics. So you guess it is coming from the Barkov irregularity, but it's not still true because Barkov irregularity only say that for some continuous function. Now we proved that the Barkov irregularity for projective dynamics for special continuous function. Okay. Yes. And I believe the idea of the proof itself is very simple. I need only 2 ingredients. So one is a hyperbolic region of the phase space, and the other is a transient region with 90 angle rotation. So please imagine that your vector v1 looks like this, and your x looks like this. So very close to the saddle fixed point, whose expanding constant is sigma, and the contraction constant is lambda. And your vector v1 is almost unstable direction. Then after, sorry, it is small, n1 iteration, the norm of this new vector is almost sigma power n1. So the finite time Lyapunov exponent in this stage positive. But the situation change after the rotation like this. Because after the 90-degree rotation, the vector is almost the stable direction. So you have maybe you have some contraction. So if you have some time scale like n2 is much larger than n1, n3 is much larger than n2, n4 is much larger than n3, then maybe you have the positive, negative oscillation, maybe. And the best toy model for this idea is surface diffeomorphism recently constructed by Guarino, Guenov, Santiago. This is a very simple model. Yes. So in this open set of R2, V, I call it V, your dynamics just linear by this hyperbolic metric. So X direction is contraction, and the Y direction is expanding, and this is dispersive. Yes, and if you define the Sn as this horizontal rectangle, then this maps into this vertical rectangle of level 2n. I mean, Sn is some interval times sigma power ni. Yes, because of this linear form. And the good things of their result, their construction is that they is integer k0 and n0. And after just k0 iteration, this vertical rectangle exactly mapped into this horizontal rectangle. And yes. Yes, exactly. Yes, exactly. Yes. Yeah. Yeah, physical measure is a Dirac measure. Yeah. You are right. Yeah. So this is not Barkov irregular. This is Barkov regular case. Yes. And the good things for me is that okay, they work math, so their return map is very okay. I don't say return map. Their map from here to here is exactly 90-degree rotation like this. So you can do direct calculation. You can do direct calculation for this model. This is a good point of this model. So you can directly check the oscillation of Lyapunov exponent. This was our first step. Yes, and we realized that the mechanism is a hyperbolic region, 90 rotation, hyperbolic region, 90 rotation, blah, blah, blah. Yes? And taking into this account, we try to consider the classical new houses example. Okay, so you have a horseshoe here. Sorry, I didn't write exactly the form of this map, but this is a linear thing. You know, so this rectangle map into this rectangle map into this rectangle. And I call it the expanding constant sigma, contraction constant lambda. And this is dispersive. Yes, and the good point of this new house example is that if your orbit come into the small neighborhood of 0, -1, I denoted by U, then the 2 iteration of your map is very simple, like this. So your unstable foliation is going to this quadratic curve, this curve going to this curve, this curve to going to this curve. So you can imagine that the image of this local unstable foliation is tangent to the stable foliation by adjusting the position by mu. And exactly what the Newhouse did is exactly found some mu such that G has such a tangency. That it's open. It's open. Yeah. So if you perturb it, you still have you can find homoclinic tangency. Yes, nice. And another nice point is that still this model is very explicit. So yeah, this motivated me to calculate something. Yes. And okay, one thing important that I should mention is that Collier and Vargas shows that by unfolding the homoclinic tangency, you can find wandering rectangle with completely controllable staying time. So meaning that for any including sequence, in my mind, this including sequence is like this. You can find diffeomorphism F orbitally close to G, satisfying this kind of property. Okay, maybe picture is better. So you can make some rectangle, a little bit small rectangle, okay? And this okay will travel along this hyperbolic region. And after n1 time, come into this neighborhood. And after 2 times, come into this here. So the image is inside RK plus 1. And RK plus 1 can do some travel with time range n2 and blah, blah, blah. Yes. And a good thing, again, is that by this perturbation, by this Collier and Vargas perturbation, horseshoe and the return, not return, tangency G2 map is not destroyed. So still your map, I would say it's return map. Return map has very easy form, just a quadratic map of degree 2. Sorry, just a polynomial map of degree 2. Yes. So this is a very good point. So if you want to consider Lyapunov exponent just derivative, just consider the derivative of this guy. Yes. Then maybe you can agree with me that the derivative of this guy is very simple like this. Yeah. And sorry, I didn't say, but the GDS model, the derivative also looks like this as a return map. And the point is that hyperbolic iteration and 90-degree rotation will make this anti-diagonal form of matrix. This makes every calculation simpler. So a very annoying term for us is that we have this here, because yeah, it's not really rotation. You know, it's just you need some curve. So you have this annoying term, and remember that the sigma is larger than 1. Yes. So if you want to say this matrix is close to this kind of matrix, then X should be very small. And the real difficult part started from this kind of computation. So we need to improve Cory-Vargas's idea and blah, blah, blah. But it's going to be very technical part, so I stop. Yeah, okay. So anyway, the idea is very simple, I want to say. So I guess it's very universal in some sense. So Lyapunov irregularity, oscillation of Lyapunov exponent can be easily observed in some sense. Yes, and this is side story, but actually we did on some two-dimensional piecewise expanding map. So probably some of you guys know example by Tsuji of a two-dimensional piecewise expanding map whose physical measure is Dirac measure. So it's not absolutely continuous. Now this case, you can also show the oscillation of Lyapunov exponent. So very similar idea, using a very similar idea, you can show it. Yes. And we are working on this conjecture. So we expect that this is actually dense set of the Newhouse open region. And any element of this set, this dense set, is Lyapunov irregular. So if you are familiar with the denormalization technique to make the big thickness or something like that, then yeah, maybe you guess this conjecture is very natural, and we are working on this. Okay, so this is part of this is the end of part 1, and my message is that in deterministic case, maybe we can find such easily we can find such a Lyapunov irregular map. So maybe we should be a little bit careful about it. Okay, so as I said, what happens if we add some noise to this system? And okay, considering such question is, I believe the importance of considering noise is very, how to say, common to you guys, because if we consider some mathematical model, it's a little bit different from the real phenomena. So noise means that the kind of difference between the model and the real. Yes. So we should consider, I think we should consider some dynamics with noise. Yes. And the surprising result of Araujo is that there's no observable Barkov irregular set for any diffeomorphism under certain type of noise. So in other words, you cannot find Barkov irregular set. In other words, your time average always exists. Yeah. For if you add some type of noise. So maybe it's natural to consider what happened for the Lyapunov irregular set. And please remember that there's no direct relationship between Barkov irregularity and Lyapunov irregularity. So this question makes sense. Okay, so one slide explanation of Araujo's result. So he consider, and we also consider T is a unit ball of a Euclidean space with a Lebesgue measure. And F is a parameterized family, C1 parameterized family. And each realization is a C1 diffeomorphism on M. And as usual, you consider IID composition like this. Then under some assumption for any almost Lebesgue almost every point, almost surely time average exists. So I want to expand these two conditions. So first condition A saying that okay, your x maybe map into I don't know, maybe here this black point, and if you consider perturbation of this guy like fn0 omega x, then point is a little bit different from this, and you take you consider all realization of this perturbation. So you consider the image of this guy. Yes. And in this sense, the noise is large, not large. Noise is not small, in the sense that this red region includes some ball of radius xi0. And xi0 is independent of x. Yeah. Yeah, so some of you already imagine additive noise. And yeah, this kind of condition is satisfying for additive noise. Yes, and this is topological side. And you also assume some measure theoretical side. So you have a natural measure on the parameter space that is an infinite product of Lebesgue measure. And you push forward these guys to this red region. Then the assumption B is this is absolutely continuous with respect to the Lebesgue. Yeah. So for me, this looks very reasonable and a very useful theorem. Yeah, he showed under this mild condition, independently of your unperturbed dynamical system, your time average always exists. Very surprising result for me. Yes. Okay. And example is, as I said, additive noise like this. And non-example is like IFS generated by some countable generators. Because if you consider IFS, this set is a countable set. And the countable set cannot include ball of positive radius. Yes, and sorry again, side story. But yeah, I'm really interested in the result. So I wanted to generalize Araujo's result and like this. So we assume that FT is continuous. So I removed the C1 for T and B, we assume B also. So I removed A, condition A, Araujo's condition A. Then the annealed Perron-Frobenius operator, maybe you can remember that these things appeared in the talk of Stefano Galatolo. Yes, this is eventually L1 compact. So you can say much more than the existence of time average in this situation. And you don't need assumption A, and you don't need regulated C1. Yes. But a little bit careful you need to be. This continuity is necessary. I can construct some example with infinitely many random sinks, but satisfying Araujo's condition A and B both. And yeah, I didn't write, but this example is very natural noise. So I put some multiplicative noise. So maybe you agree that the multiplicative noise is the second natural noise than additive noise. And such even natural noise, you should be careful for something. Anyway, sorry. So coming back to the Araujo setting, I mean that the C1 family and the condition A and B, we can show Lyapunov exponent always exist. And furthermore, the candidate is only finite to many. Yeah. So sorry, it looks a little bit technical, but you can find the candidate of Lyapunov exponent with double index I and k, and both sides are finite. So this candidate is, oh, sorry, this is better. This candidate is finite. And for almost every x and almost every omega, your Lyapunov exponent exists. And like the oscillated splitting, you can find Lyapunov oscillated flag like this. Yes. So conclusion, this time, this stage conclusion is that, okay, in the deterministic case, we should be very careful because my impression is that we can find many dynamical systems for which Lyapunov exponent oscillate. Yes, but if you add some noise, very natural noise, I say, then Lyapunov exponent always exists. This is conclusion. Okay, but this maybe disappointing point for me is that the proof is too elementary. And sometimes happen. So, okay, the things is very easy to explain. So if you add the arousal condition A and B and the continuity, then you can find the stationary measure, find only finitely many stationary measure. I wrote it to mu1, mu2, mu-L, okay? And take a point, omega, sorry, take a point x, Lebesgue almost a point and take a noise level omega. Then your random orbit hit the support of these stationary measure in a finite time. Yes, yes, finite time. Then this is a stationary measure. So you know the story. If you consider the skew product map induced from the random dynamical system, the product map of stationary measure and this measure is an invariant measure, right? So you can apply every algorithmic theorem. So this is a story in the random case. Yeah. So if I draw again, yeah, if you introduce some skew product map like this, then you can find the algorithmic invariant in the usual sense, invariant probability measure, finitely many invariant measure. And for any point, your orbit land into some of these guy. So if you apply Barkov's algorithmic theorem, then you can get Araujo's condition. If you allow the oscillated algorithmic theorem, you can get our conclusion. Only that. So originally, we had this kind of things in our mind. And originally, we thought we need to modify Araujo's argument. But yeah, his paper is like 60 or 70 pages. And read carefully, took like 1 month or 2 months, and we realized that everything was written already. So I don't want to say it's explicitly written, but you are careful reader, then you can say, this is Araujo's result. This is Araujo's result. Yes. Okay, so sad story again, but this is almost the final. Okay, so the point is that if you assume condition A, B, and continuity, then you can get kind of a nice property and apply algorithmic theorem. So maybe you feel that, again, using the annealed transfer operator, annealed Probabilistic operator, you can formulate this property. And yes, we can do it. It's called the so-called maximal support property in the theory of a mean algorithmic theory. Yes. So yeah, actually we obtain equivalent condition for this nice property in the sense of annealed Probabilistic operator. So I mean, you can generalize Araujo's result more. Yes. And we also did some example, which is not absolutely continuous, so violate Araujo's result, but still Lyapunov exponent or converge, like that. Okay, that's all. Thank you.
Questions? Any questions? Yes.
Yeah, so one question is we can also study cases where you don't have positive if you don't have positive measure of irregular points, can you say something about the Hausdorff dimension? You know, can you look at attractors like the head-on attractor and
He did.
is it? Did it?
Yeah. There's
Okay.
some, I would say, many literature did by Paolo Baranda, Shueting Tian. Yeah, considering even hyperbolic situation, you can find a full dimension of irregular set.
Okay, but so what about in the case in which you have positive measure of irregular sets? Can you find some examples with interesting dynamics? You know, can you say some? Well, for example, the new house.
Yes.
It would be interesting to know what is the dynamics of this set of, you know, what. Say something more about the dynamics.
Something more about the dynamics.
Yes. It's an invariant set, I guess, right? Because by definition it's an invariant set, right?
So you were talking about without noise.
Without noise.
Why you think the new house example has okay, so on the horseshoe we have an invariant measure. So on the horseshoe we can understand the dynamics. And the Lyapunov irregular set in that case is a wandering domain. Yes. And the time average, as I said, sometimes does not exist, sometimes exists. So my guess is that on the wandering domain, we cannot find the invariant measure. Maybe it's not your question, sorry.
Giorgio?
Can you elaborate a little more on your example with countable many IFS maps? How do you fit into a dynamical setup? You can give a few more details, please.
Oh, sorry. IFS case?
Yeah, your example of
yeah, IFS
you briefly
is not
mentioned IFS with countably many maps.
Yeah. This is a non-example. So I cannot apply. I cannot apply these things. Yeah. Sorry. Sorry. My English is. Sorry. Maybe it's not correct English.
Paolo?
So in the random case, you take omegas, which are generic for the noise.
Yeah.
So the empirical framework. So can you say something about non-generic realizations?
Yeah, interesting question. Honestly, I didn't consider about it, but yeah, very natural question. Maybe, but it should be very difficult because in your mind, probably you have the example like Barrera shredding, but they need some kind of hyperbolic structure. And okay, this noise dynamics is similar to such one, but we have one more dynamics on fiber component. So I don't know, this can be challenging, but it's interesting. Thank you.
Thanks.
Any more questions? Well, then let's thank our speaker once more.
So I'm happy to introduce the last speaker of this wonderful conference, with Mark Demers. Well, has also been the Georgie Fellow some time ago.
Yes.
And so I'm very happy. I mean, he has visited several times since, but still, once again, it's great to have you here. And Mark is going to talk about projective cons for dispersing billiards. Okay.
Thank you very much. Yeah, thank you for the invitation to come here. It's always a pleasure to be back in Pisa. especially after all the shutdown of COVID, and a special pleasure this time to wish happy birthday to Ian Matt. You must be sick and tired of hearing it by now, but happy birthday anyway. And thanks to all of you for sticking around for the last talk. And now I know you're the serious. Oh, right, the three of us, exactly. Okay, good. All right, well, you may recognize some topics here then. All right, so yeah, so I want to talk about projective cones, which is kind of a, this Hilbert metric applied to billiards. And so as a motivation, which is obviously not the only thing you could do, but just as a motivation for this, you might consider, say, the aperiodic Lorenz gas. So a periodic configuration of scatters, it's been very well studied since the 60s, since Sinai, right? Because with a periodic configuration, you can just take a quotient on, say, a torus, and then you have a compact phase space, and you can study a transfer operator and find it. It has a smooth invariant measure, and lots of statistical properties are known in the periodic case, and in particular in the compact case. In the aperiodic case, there's a lot less known, so just a few references, and this is not a complete list, so just a few references. But just to say, in the finite horizon aperiodic case, Marco Lenci proved for some special models typicality of recurrence, and that recurrence was equivalent to ergodicity in the infinite measure setting. More recently, Trevino and Zalrovitz have, for some sort of not so aperiodic, but having some long-range structure, some sort of linearly repetitive long-range structure, they're able to embed the aperiodic configuration in a tiling space, and by doing that, create a compactification. So it's kind of like what you would do in the single cell type dynamics. You have a compact space again, and then on that compact space, you can start to prove some properties. So they prove, for example, some mixing and K-mixing property for this tiling system. In the infinite horizon case, one thing you can do is take the limit as the size of the scatterers go to 0, called a Boltzmann-Grad limit. And so going back to some classic work of Galabotti and Spohn, and then Boldagrini, Bunimovic, Sinai, followed up in slightly different assumptions, but they derive in the 0 scatterer limit some kind of differential equation, right? That's this linear Boltzmann equation for the particle density. And then more recently, Markloff and Strombergson did kind of generalize, they get kind of a nonlinear equation for some both periodic and aperiodic configurations. And there they have some condition on long range interaction. So almost periodic, sort of quasi-crystals. So those are some existing works, and it's just a motivation, right, for what, why you might want to look at cones for these billiards. So this is kind of a toy model that Marco Lenci put forward in 2006, and also was used more recently in a paper by Romain Aimino and Carlangelo in this kind of deterministic walks in random environments, I think it's called. So here you throw down some periodic arrangement of scatterers on, say, a square lattice, and then in the center of each one of these cells, you put a disk, right? So these cells are kind of separated. You can kind of take one cell. And in a cell, you have the central scatterer that could have a different position, right? A different size, maybe a different position. If you choose it to have the same size, then in each cell, actually, you have the same arc length all the way around. So you can think of the billiard map on the same phase space, because the billiard map, when you look at the collision map, the Poincaré map, it only cares about arc length. That determines the phase space. So you could think about a sequence now of billiard maps on a single phase space if your arc length in each cell is the same. And that's a situation in which now you're thinking about this kind of, right, a concatenation of different maps that maybe change a little bit or maybe change a lot, depending on how you allow that central scatterer to change. That's going to be maybe put down by some random process. And then you're going to, as you move from one cell to the next, you apply a different billiard map, a certain number of iterates until you move on to the next cell. And so that's the dynamics. And of course, we're interested in transfer operators, so that you just have the concatenation of transfer operators, again, sequences. So this is just a motivation for why, one setup in which you might care about sequential dynamics for dispersing billiards, if you want to try to understand at least some toy models of the aperiodic Lorenz gas. Our transfer operator is just going to be that, very simple, because The billiard map preserves a smooth invariant measure. If you take the smooth invariant measure as your conformal measure, why not? May as well take that instead of the Lebesgue. Then your Jacobian is 1. And so your transfer operator just has this very simple definition, and you can work with it pointwise. Okay, so so the main technique I want to talk about is this cones. So here, just give a general definition of a cone. Basically, you have some set that is well, closed convex. So I didn't define convex, but you know what convex is. So a cone just means you can multiply any element of it by some positive multiple, and then closed means in this sense that if you have some here, some linear combination, right? G plus alpha Fn, alpha n is alpha n f. Alpha n is just a sequence of real numbers that converge to alpha. Then that limit, right, should also be in the cone. Union may be 0, right? So we call it closed even though it doesn't contain 0. And then you can define a partial ordering on the cone here by just say, you know, so f precedes g if g minus f is in the cone union 0, and then you use that partial ordering to define the Hilbert metric. So you're just taking the sup over all the multiples so that lambda f stays below g, the inf over all the multiples so that mu f stays above g, and then that ratio beta over alpha, that's your log of it, that's your projective metric. So you can see it's projective because if you multiply f or g by, say, you take 2f instead of f, it doesn't change this ratio, right? So any multiple of f will just give the same distance to g. And in fact, if you choose g equal to a multiple of f, you get 0 there. You'll get a 1 for the ratio and 0. So it kind of quotients along lines. So the goal here, following, I think that one of the first dynamical applications of this that Liverani did back in '95 was to some smooth hyperbolic and piecewise hyperbolic maps, is to try to show that when you iterate this operator enough times, this one, right? And so here it's not an iterator of a single operator, but some sequence of operators, then it has finite diameter in the cone. And that will tell you that you have some sort of exponential contraction, right? So if it's a single map, then you have exponential decay of correlations. If you have a sequence of maps, it's something else called exponential loss of memory. You can kind of compare two different starting points, right? And they will contract exponentially fast. And you can do this with respect to the invariant measure, SRB. That's that smooth invariant measure. It's cosine phi times Lebesgue. Or you can do it curve-wise. So on stable curves, as you see, the cones are going to be defined an integral on the stable curve. So you can kind of do it standard pairs-wise. If you've seen standard pairs, evolution of densities on standard pairs will also converge like this. Okay. So this, if you impose a condition of slowly varying configurations, then this was studied in a paper by Mikko Stedlin, Lai-Sang Young, and Hong-Kun Zhang. 10 years back, actually, in which they have a configuration of scatters. It's in compact space, though. It's on the torus. And then between collisions, the scatters are allowed to rotate and move a little bit. Then you have another collision, then the scatters can move a little bit. Then another collision, and the scatters can move like that. So there will be some overlap here in terms of these results that they got. Our situation is a little bit different in the sense that we allow extended systems and also large movements of scatterers. But there is some overlap there. And they used coupling methods. Okay, so what we'd like to do to set up these cones is fix certain parameters that are geometric in nature, just relying on the billiard table, and saying that, look, if you just fix a certain set of parameters to the billiard table, then all your billiard maps that you can associate with these, they'll all have a uniform set of properties. And so we don't really care which map we're applying at any given time, as long as they satisfy this uniform set of properties, they'll all contract the same cone, they'll all evolve kind of in the same way that we want. So you have to choose 3 constants, and then everything is determined. So the 3 constants you have to determine are tau star, k star, and e star. Well, I lied. There's 4 constants. You first have to choose the number of scatterers. Okay, but that gives you a phase space. Once you do that, then you choose these 3 constants. So what are they? So tau star is going to give you an upper and lower bound on the free flight times on the table. So the minimum flight time and the maximum. Yep. In that example, right. I mean, this is a more general setup. So all I'm doing is just fixing a common phase space. And then I'm just going to put some abstract class of maps on that phase space. But yes, if you want to apply it to the aperiodic Lorentz gas, then it would be in a Marco-Lenci model, it would be exactly fixing the same number of scatterers in each cell. Each cell should have the same number of scatterers, right? Even though their arrangement can move, right? So that will not affect the phase space. It will affect the map, but not the phase space. Right. So tau star will be your min and max upper and lower bounds on the free flight times in the phase space on the billiard table. And so in the aperiodic case, in one cell. K star will be the upper and lower bounds on the curvature of the scatterer, the boundary of the scatterers. And E star will be the max on the C3 so the third derivative, which you need in order to bound the curvature of the stable and unstable manifolds, which is nice to have. So you just need an uniform upper bound on the third derivative of the boundaries of the scatterers. So if you fix these three quantities, then you can study this class of billiard maps with these three quantities fixed, and they all have uniform properties, right? So those are the three numbers that geometrically determine everything else. So for example, they give you, these are not assumptions, right? These are consequences of having fixed those three numbers. They give you cones. So you have hyperbolicity away from the singularities. Singularities here come from the tangential collisions. So as long as you stay away from tangential collisions, you can define, you see the cone in terms of just tau star and K star, right? And then, oh, that's a typo. That should be a negative K star. The stable cone has a negative slope, and then flip it around, make it everything positive is for the unstable cone. And there it gets strictly contracted on the dynamics, right? Backwards for the stable cone is strictly contracted, forwards for the unstable cone. And then you have minimum hyperbolicity, lambda. Lambda, the minimum hyperbolicity, also expressed in terms of K star and tau star. So everything here, all the hyperbolicity is determined by that. You can just do it. This implies that you can have families of stable and unstable curves. So what these families are, WS and WU, they're not stable and unstable manifolds necessarily, but they're curves that lie in the right cones. So WS will lie in the stable cone, WU will lie in the unstable cone. They'll all have uniform bounds in the curvature that depends on E star. And then you can use a common set of homogeneity strips to control distortion, because obviously you're going to get big derivative blow up of the derivative as you approach tangential singularities. Tangential singularities happen when phi is close to pi over 2 or minus pi over 2. And so that's where you chop up your phase space into this countable collection of homogeneity strips. These maps also preserve a common invariant measure. That makes certain things convenient. It's not necessary at all. So particularly when we open these things up, you'll see we think about open systems with holes. Open systems don't preserve invariant measures. Or I mean, they do on some Cantor set, but they won't preserve the smooth one, and that doesn't affect the cone technique at all. So that is convenient, but it's not a necessary property. Yeah, Paul. Singularities will vary as along the sequence of maps, you will have a sequence of singularities. Yes, exactly, right. Yep. Okay, so right, bounded distortion. So here you actually can show that, so of course you have bounded distortion for one map, but here you can actually show that you have a sequence of maps. If your orbit stays in a common set of homogeneity strips, then you can just inductively prove that, in fact, these ratio of this, in this case, ratio of stable Jacobians has this bounded distortion properties, even along a sequence of maps. And this sequence of maps does not have to be close together, right? They're just drawn from this family with tau star, K star, and E star fixed, but they don't have to be close as maps. Still, they will have their concatenation will have bounded distortion. And then you have a uniform one-step expansion. So this is kind of Chernow formulation of the requirement that hyperbolicity beats complexity. So hyperbolicity beats the cutting. And this theta star, call it star again, because it is only depending on those, right, uniform properties of the class of maps. So it's the same theta star for all the maps, and you can choose a single length scale for which this works. So this is basically, you take a stable curve, you map it back, it gets cut into a bunch of pieces by the singularities. You look at the average contraction in each stable piece, you add them up, and the contraction should beat the cutting, meaning that that sum is actually less than 1 for sufficiently short curves. So that is not an assumption, but a property that's approved property for this class of maps. And here we just listed in the sense that you can choose everything uniform for this class of billiards. So in particular, you can boost the, you can use the bounded distortion and the uniform one-step expansion to boost to what's called a growth lemma, right? So if you've seen billiards for a single map, there's your kind of, you take a power of a single map and you can define sort of what we call generations of pieces, right? You just, you pull them back one step, they get cut, then each piece in turn you pull back and they get cut. And so you end up with some nth generation of pieces here, this GNW. And you subdivide long ones to be between length delta 0 over 2 and delta 0. That's so that you can use the one-step expansion, and then you can iterate the one-step expansion and get this classical growth lemma. But here the growth lemma has been boosted to be along sequences of maps. And again, the constants are uniform for the class of maps. It works for concatenations of maps that are not necessarily close together. You still have growth lemma, so you still have control of complexity. Okay, so and that actually is back in when we were doing some random perturbations with Hong-Kun. Zhang and I worked out this stuff, and we get to use it. It's always fun when you get to use something that you've previously proven. Right, you put in all that effort, and you're like, wow, when can I use it again? Yeah, so it works now for these cones of the sequential billiards. It's it was already done. Okay, so for most of what we do, we don't need to have the maps close. But sometimes we do. And so for some mixing argument that we're going to need to construct, we do need to have them close. So it would be nice if maps were close in some sense, if the tables were close, right? If the scatterers were somehow close in position. So that's how we're going to define closeness of maps. It's just you take Q and Q tilde, two billiard tables, and you're going to measure how close they are. So how can you measure how close two billiard tables are? Well, maybe we parameterize the boundaries to some functions. And then we ask those parameterization, we kind of pair them up, and we ask how close are those parameterizations. And then you maybe take an infimum because, I don't know, maybe you paired this one with that one. That wasn't such a good pairing, but maybe there's a better pairing. And so in the infimum of all the pairings you could do, you look at the difference in the C2 norms of the boundaries of the scatterers. Remember, oh yeah, the boundaries of the scatterers are all C3, so you're only asking them to be C2 close. And that's your distance between two billiard tables. Now you'd like to convert that to maps, but as Paolo pointed out, well, hang on, you change a scatterer, you're going to change the location of a singularity curve, right? So that's not going to be so close. Obviously, there'll be some points that go really far apart. They have very different orbits. So that's true. So, but there is still some control. So you take two billiard maps, T and T tilde, that correspond to Q and Q tilde, and if the distance between Q and Q tilde here is less than epsilon, where's the button? Epsilon, right? Then you get some stuff. So you have to look outside a neighborhood of the union of the two singularity sets, because obviously the singularity sets will shift. And if you're on one side or the other side of the singularity curve, you can get mapped to very different places. You can't expect to have images that are close by. But okay, close one eye. Don't look at an epsilon neighborhood of the singularity set, of the union of the two singularity sets. And then how do the dynamics compare? Well, then the pre-images of points should be epsilon close. The distortion should be not bounded. And then actually this is kind of C1 close. Square root of epsilon is good enough. So you do get some kind of C1 closeness if you have tables close by and you kind of close one eye and don't look in an epsilon neighborhood of the singularity set. So you can kind of throw out some piece, as you see, we're going to be integrating anyway. So you can throw out some small part and then the maps are close. Other than that, this stuff is always going backwards because the transfer operator is always oriented backwards under T inverse. So you could make analogous statements for T going forward, but we're just always orienting stable curves going backward rather than unstable going forward. Okay, so let's define our cone. So we want to integrate along stable curves and against some appropriate test functions. So if you've seen standard pairs, then this is going to seem very familiar to you, because in standard pairs, you take an unstable curve, you take some log Holder density, you push it forward, you show that it stays in the same class, and you do these coupling arguments that way. This, we're going to have a similar thing. Our test functions are going to be some kind of log Holder test functions. We're going to be on stable curves, apply the transfer operator, change variables, that'll map the stable curve back, and that will evolve nicely and stay in the kind of the same class. So it's really just, I mean, it's basically standard pairs for T inverse. That's that's kind of what it is. Okay, so here's a cone of test functions. You can see we're just going to take a cone of test functions that's log Holder continuous. So A is the Holder norm, alpha is the Holder exponent, and that's a class of test functions on those stable curves. This cone of test functions will be contracted by the hyperbolicity of T, all the T in our class F, once we set that tau star, K star, and E star. And so eventually you choose, I mean, I'm not going to really get into it, but eventually you choose alpha to be like less than a third because you have the homogeneity strips, and A should be large enough that the distortion constant, and you get kind of contraction plus distortion, and you want that to be less than A. So A is large enough compared to the distortion. Okay. So ideally, what we'd like, right, in this kind of setup in the phase space, you have a stable curve, call it W1, and another stable curve, call it W2. And then you'd like to compare them because, well, in a hyperbolic, for a hyperbolic map, right, you would kind of expect that the action of the dynamics should be smooth in the unstable direction. Here, the unstable direction is going to have kind of positive slope. So transverse to these stable curves, you have some regularity for the map. Well, if the map is map and for elements of your cone, so if this regular in this direction, then the integral on a curve and another one that are kind of close, they should vary, right? They some Holder way. I mean, they should be close, right? If the curves are, if these two stable curves are close, then the regularity in the unstable direction should make those integrals close. And so we're going to try to capture some of that in these definitions here. We're going to express each of these stable curves as some graph over the R interval because they all have bounded slopes between 0 and infinity, bounded away from 0 and infinity. You can express them as graphs over the R interval. The R is just the horizontal arc length. Phi is the vertical angle. And then you can say that the distance between two curves is, say, maybe on the common interval where they're defined, you ask them the graphs to be C1 close, and then maybe there's some overlapping bits where they don't match up. Okay, so add the symmetric difference of those intervals. So in this picture here, maybe, right, there'd be some part here that didn't match up and some part here that didn't match up. And we should add that distance. And so the sum of those two is going to be the what we call the distance between two stable curves. And then between test functions, well, once you have a common R interval where they're defined, you can just project them down, right, to the R interval and ask them to be, say, some kind of Holder distance apart. So beta here will be some Holder exponent that's less than alpha. And here I throw in the Jacobian. This is the Jacobian of, here it is, just mapping from the R interval up to the graph. So why do you want the Jacobian in there? Well, because if the distance is 0, it's not so much that you want phi1 and phi2 to be identically the same. You want them to integrate to the same thing. And so sticking the Jacobian in there means that the distance between two test functions being 0 means the integral of this one will be equal to the integral of that one. Okay. So now we want the cone. So the cone is we have kind of two length scale, well, two families of stable curves. The stable curves without the minus below is just going to have basically length scale delta, so between delta and 2 delta. And then with the minus below is anything shorter, 2 delta or shorter. So the WS minus includes the WS. And we're going to define something that looks like a norm. It's not quite a norm, but it's going to be a relative ratio of how mass is distributed for elements of our cone. And so here this is just projective, so we're dividing by the integral of phi. But what you're really looking at is kind of some average value of integrals of f on curves of a certain length scale. So this is not the minus, right, but curves of length between delta and 2 delta. And you can take the infimum of all those averages or the supremum of all those averages. And that'll be this triple bar minus and plus. And those are kind of telling you how the mass is distributed. If the inf is 0, that means your function f is not seeing a certain part of your phase space, right? There's some place where you have 0. If it's positive, if the inf is positive, then that means your mass is equally distributed. And so this is going to be a condition that we try to enforce in the cone to get the diameter of the cone finite, is to get that inf to be positive, and not just positive, but not too small compared to the ratio between these two. It's going to be bounded. No. I don't want to take a WS minus for these. These are going to be averages on curves of a definite length. So this one. What's that? This is a supremum, and that's an infimum. Yeah. So I'm looking at the smallest and largest possible averages here on these curves of a fixed length, scale. And now the cone has these 3 parts: red, blue, green. Well, we're in Italy, so I had to use the red and the green. And white didn't show up well on the slide, so. Yeah, black background, right? Okay, so the red one is what we said before. It's if the soup is bounded by some constant times the inf, then you have full support. In particular, it forces the inf to be positive, and that somehow the mass is spread evenly. So that's the red condition. The blue condition says integrals on short pieces is small. It's a kind of control on, if you use one of these powers, this is an average integral down here, but it's basically saying that the integral of this thing on a short curve is basically like w to the q. And so it's saying that you can control the integral over short pieces. When you iterate these dynamically, of course, you're going to get short pieces because of the discontinuities, but you want to know that they somehow are controlled. And that component of the cone is going to control the short pieces. And then the green is what we were talking about here. It says that the integral over 2 close stable curves should vary kind of Holder continuously depending on the distance between the stable curves. So that's what this says. The integral over 2 stable curves should vary Holder continuously, that's the gamma, depending on the distance that we define between the 2 stable curves. And so that's kind of this Holder. It's a weak sense of Holder regularity in the unstable direction. Integrated, obviously, not pointwise. Pointwise things fall apart because you have cutting. If you measure on 2 sides of a cut, there's no, pointwise, you don't have any continuity. But integrated, subdividing curves, controlling the pieces that you can't compare with the blue, you can kind of get this weak notion of regularity. So those are the 3 elements of the cone. They play pretty different roles. So our goal, obviously, is to get the 3 parameters there, C, A, L. Each one is just for one of these components. L controls the red, A is the blue, and C is the green. And so we want all 3 of those parameters to contract. If you can do that, you can show that the diameter of this, with the 3 contracted parameters, this is finite diameter in the original cone. So that's the goal. And you have to prove that, but you can do it. And so then, fine, now you have contraction and projective metric. So why do you get to say that something like an integral, which is not projective, right, contracts? So you have to relate the difference in integrals to somehow this difference in projective metrics. And this type of relation follows because you have some kind of ordering. Although the integral is not projective, but it does follow the ordering. If f precedes g in the cone, then actually for some class of test function psi, these integrals are also ordered. And that's the consequence of this plus minus stuff that sort of dominates the integral. And so that is the sort of dominance that you need in order to say that your projective metric in the cone will imply contraction of integrals. So that's the goal, and it works in sort of 2 steps. The first step is that you can get C and A to contract. So C and A are the blue and the green bits. The blue-green was the control of short pieces. The green bit was the contraction of close stable curves. This contraction is just like proving Lassotti-York inequalities in the sense that it's just the local hyperbolicity of the map that forces these 2 parameters to contract. And so This sequence of maps does not have to be close together. You can draw any sequence of map from this uniform family, right, with tau star, k star, and e star fixed, and you will have those uniform Lorenz inequalities, and you will have the contraction of those two hyperbolic parameters. The problem is the third one, the L, the plus minus, right, the triple bar plus over the triple bar minus ratio, that's not a Lorenz thing, because that relies on mixing mass around your space. So that's a mixing property, right? And that's not a local contraction that depends on hyperbolicity. So to get this one to contract, then we have to use something stronger. And the thing that we have to use that's stronger is that we have to draw maps that are close together. If we want them to mix, we somehow get, C supports that cross, then we need to draw sequences of maps that vary slowly enough that we can force different Cantor rectangles essentially to cross one another and mimic a kind of coupling argument in order to control that ratio. So that's the whole second part of it. And if you've seen coupling arguments, it has this type of flavor, right? You fix a certain map, which if you're doing coupling could just be your map, you're just looking at powers of the map. But here we can fix a single one, and we're going to construct a Cantor rectangle using the stable and unstable manifolds of that map. And then we can force any stable manifold, any stable curve, of length at least delta to cross that Cantor rectangle in a finite time, n, that depends on t0. And then if you perturb that, once you have that time n, then you can choose an epsilon so that sufficiently close billiard maps or sufficiently close billiard tables will also have a component of a stable curve crossing at that same time. And so that's the sort of perturbative version of that argument, and why we need to draw a sequence of maps that are close together in this sense, so that that mixing property is just perturbed and still is kind of robust, right? Because as long as you cross this rectangle, it doesn't really matter how you cross it, right? But clearly under perturbation, if you properly cross it somewhere in the middle, you perturb a little bit, you still be crossing it approximately in the middle. And so that's the argument that makes L contract. And so the theorem is this, that, yeah, we get this strict contraction of the cone, but you have to choose an admissible sequence. So what we mean by admissible is just one that this is a random sequence of maps from, or an arbitrary sequence of maps from the uniform family, but kind of blocks of n at a time should be drawn from epsilon neighborhoods of a fixed map. So you kind of go n blocks to make the L contract, right? Then you can change your maps a lot, but then the next block of n should be drawn from an epsilon neighborhood, and so on. So between blocks, you can change your maps a lot, but in a block, it should stay approximately equal. Right. So, and it's exactly this kind of large jumps between blocks that allow us to apply, at least sort of apply, this result to the aperiodic Lorenz gas. You'll see how we have to modify it. It's not quite satisfactory yet, but we'll try. All right, so back to our example. So our toy model was this one, right, of Lenchi, where you throw down some scatters in some square lattice, and then you put a central scatterer in each cell. And now you look at these transitions through the cells, right, from one cell to the next, and you realize that, well, you can't, if you just leave them open all the time, then you can't really control the number of bounces that you take in any one cell. And if this scatterer may be very far from that scatterer in position, they may not be close together. So maybe only 3 bounces and you come back, or maybe just 1 bounce and you come back. And so we do this thing called lazy gates, which means that the gates stay closed. You put these kind of red gates in. They stay closed for capital N iterates. Then they open. Particles can move as they like. And then you close the gates for another N iterates. Then you open them again, and you close them and open like this. And they're lazy because they're closed more often than they're open. And they take a while to open. But it's that closing time that lets you get the strict cone contraction. And so you can set up, right? So in this setup, you can set up things kind of formally, which, yeah, we can run through that. So yeah, I mean, you kind of, obviously you have to put some limits on the placement of the central scatterer because you don't want these to touch, right? So you want to, there's be some allowable set of configurations, and with that, within that allowable set of configurations, you just arbitrarily assign, scatterers to a central scatterer to each cell. And so this is your collection O will be all the allowable configurations of this central scatterer. The allowable configurations will obviously fix a uniform tau for your lower bound on the flight time. That's just a minimum distance the scatterers have to stay apart. But in this setup, then, the nice thing about Lenchi's model here is that the phase space and the gates are the same for any choice of O, because moving around that central scatterer doesn't affect the location of the gates, right? The gates are disjoint from the central scatterer. By the gate, I mean the transition from one cell to the next. And so the associated billiard maps all belong to a uniform family. Since in this model, they're all disks. E star, you can just choose to be 0. There's no problem with, the third derivative is just not there. They're all just circles. And so you have some, countable collection of scatterers, permissible scatterers in every lattice cell. So you just O to the ZD. And then, of course, you have just translation, right? As you move from one cell to the next, you have just natural action of the configuration by translation. And so here's your 4 gates, which you can just call W0 is if you don't move. W1 is if you say go 1 step to the right. W2, 1 step up. W3, 1 step to the left. W4, 1 step down, right? Those are kind of your 4 unit vectors that you can go. And then you have some sort of extended dynamics on Z, which is your integer position, right, on the lattice. Your Z2 position. And then X is your point in the phase space of that cell. And so you take n steps in one cell, which we'll call S, C, and then if you're not in one of the gates, you just stay in that cell. And if you are in one of the gates, then you update your Z coordinate according to the W, right? According to which are you moving one cell up, one cell to the left, one cell down, one cell to the right. That's just a lot of notation to express something that's sort of intuitively very clear, right? But you have to set up a system now with 2 coordinates, a Z and then an X. The Z tells you where you are in the lattice, and then X where you are in the phase space. So you have some kind of macroscopic dynamics that tells you kind of evolution of your cells, right, as you go through this lattice. Okay, so suppose we have some probability distribution, right? And you can choose, so we want some sort of just put down some random collection of central scatterers. That'll be our omega, and that'll be give us sort of probability distribution of the scatterers. And then our change of cells cumulative at time n is just the sum of the change of cells. If we assume we start in 0, 0, then our n after n steps, it's just the sum of the change of cell unit vectors. And then we can interpret this probability of following a sequence of cells as, well, integral of a bunch of transfer operators, right? Because if you go through that sequence of cells, then that means you must hit this sequence of gates at these specific times, right? The gates are just the preimages on M, the phase space of those little red line segments. And so if you, so it's just a product of characteristic functions, and then changing variables, you just have a bunch of transfer operators. And these transfer operators, notice, are, right, they're kind of abbreviated here, this LG, so the Gth gate. But what does it mean to go through the Gth gate? It means you have an indicator function you're applying at that last steps, you're going through that gate, but for the n-1 steps before you stayed in, or and then the gates close, and so for n-1 steps after, you stay in that cell, right? And then it opens again, and you have a new indicator function, a new transition transfer operator, and then n-1 steps in the new cell, like that. So it goes like this, and you can see that when you're multiplying indicator functions, you've got another thing going on here in the code. No one said that the multiplying by an indicator function was a bounded operator in your cone, right? So that's something else to prove. And there we use the fact that you can do some transversality arguments with, well, not the gate, actually, indicator function of the gate is not so good, but if you apply the inverse image to it, since we change variables in integral, this does have good uniform transversality properties. And so we can show that that concatenation of operators does contract the cone. It's really an open system if you think about, but with a very large hole. Because each one of these transfer operators is a billiard map with a hole, where the hole is is not the gate, right? So this should be the indicator function of the complement of the whole, which means that the whole is the three other gates you didn't go through, and you stayed by going through that gate. So that's really that. So it's kind of billiard maps with very large holes, and you're sort of following the path that you would need to survive along this itinerary, sort of not falling into the hole, but passing through the right sequence of gates. And so then you can get the sort of exponential contraction that you want. Just reinterpreting these conditional probabilities in terms of the integrals of transfer operators, you get this exponential memory loss. And which is, so for this one, it says if you have kind of different amounts of memory, right here you have all n steps of memory, here you have n minus m. And so you get a exponential rate of contraction depending on the difference in time steps. Or you can think of memory loss as same amount of time, but two different starting points, f and g, and then you have a memory loss statement that's kind of like this. If you flow forward n steps starting at g, or flow forward n steps starting at f, both f and g starting in the cell 0, 0, then you get exponential memory loss with rate theta to the n. So these are just formal statements of those ideas that once you adopt the lazy gates, you can get this exponential memory loss, both versions of it, for this aperiodic toy model of an aperiodic Lorenz gas. And I'll stop there.
Thank you very much. Questions?
So, Mark, I remember asking this question already, but with a different perspective. So, but now in case of toy model with lazy gates, if you rather, I don't know, position your middle scatterers with some like epsilon closeness to each other. So in the sense that, for example, you take 4 lattices close to each other, and then the middle scatterers are positioned somehow relatively epsilon close to each other in the distance, like relative to the big scatterers, then maybe there would be some kind of uniformity in the sense that the particles spend some uniform time in one cell and then the other cell, because there's a drastic difference in without the lazy gates in the time that it spends in one cell and then the other because of the position of the scatter. But if there is some kind of uniformity, then maybe there is some kind of uniformity also in the time that it spends in a cell at a time and then the neighboring cell. And then maybe you don't need the lazy gates model and
that would be nice, but yeah, I mean, so there are some obviously technical difficulties with that. So if I mean, in some average sense, what you're saying is right. If these two scatterers are close together, then the distribution here will be close to there. But of course, there will be some trajectories which have some bounce back, other ones which go. And so since we're considering evolutions of stable curves one at a time, that's the kind of the definition of the cone is strong in that way, in the sense that you have to control the evolution on every stable curve individually. Each of them you have to show do this the same thing. So this one that does a bounce back versus another one that stays 50 times in here and then comes back are going to have very different futures or paths, I guess, because we're iterating stable curves backward. But and so so even though on average of all the initial conditions they will be doing similar things, the uniform control on each one, the evolution of each one could be very different. And this is the difficulty we have in controlling that and why we adopt the lazy gates. So I agree, it would be nice to drop it, just not sure how to do that yet. Yeah.
More questions?
Thank you. It's a related comment to the question. I remember 25 years ago, Carlangelo sent me some notes to have no subcone. It was the name of the thing, and it was done to prevent this problem of this covering assumption that and to have only topological mixing. So the idea was only to use some conditional expectation on a small partition.
Okay. I'll ask Carlangelo about that. I have not seen the no soup cone.
Yeah.
I mean, actually, this is a little bit Carl. So you remember Weil's talk? He had these norms, right, for these hyperbolic maps that actually try to integrate on the whole manifold rather than on stable curves, right? So, so the sort of the Guzel-Livrani version integrates on stable curves, and now Carlangelo is trying to look for something that's more like Baladi-Suji, which is integrating on the whole manifold. And so maybe, yeah, maybe if one can push that direction, one get a version of that. The problem with that is that it hasn't been done so far. So, I mean, there's some problems with implementing with systems with discontinuities. So the curve-wise approach is simpler when you've got discontinuities. That's been the trade-off so far. But yeah, right. Yeah, maybe. Thanks.
There was another question. Cecilia, maybe. Yes.
Thanks, Mark. And I think it's perhaps a little related. So could you say a little bit more about that capital N?
Capital, that is the one sort of non-constructive piece of data, right? That's the problem. So these other stuff, when you do this contraction of C and A, you know exactly, I mean, it's the Lossori-York type thing. You know exactly the dependence on the hyperbolicity of the maps, and so you know the dependence on the geometry of the table, because you can express all those constants in terms of the tau, the kappa, you know, all these things for the table. But the L uses a mixing time, and so this is really saying at a length scale delta, you have to know what is your mixing time at a finite scale, right? That's really what N is. It is when can every box more or less of dimension delta squared see every other box of you know, delta by delta. And that's, I don't know how to quantify that, right? In terms of the geometry of the billiard table. So that's why we fix one map, T0, we have an N for that map, but we don't know how to quantify what that N is depending on the map. And then we choose out a neighborhood of that map. So it's a mixing time. And I don't think I mean, even in the coupling arguments for billiards, for a single map, we don't have a good control on what that mixing time is. If we did, we could get a very good, you know, good bounds on decay of correlation, say, for a single map, but we don't have good bounds on that. So, yeah.
More questions? No? Okay, then we can thank Mark again.
Thanks.
And since this is the end of the workshop, I also take the opportunity to thank all of you for coming here and our speakers, our colleagues getting nicely older so that we can also have more excuses to meet. And I also wanted to thank the Centro de Giorgi and the Scuola Normale for hospitality and the staff for all the work they made, and the organizing committee. So let me call them name by name. So Carlo, there, and Claudio, Gigi, hiding, but also Gigi, and finally Sandro, whose passion for mathematics and mathematicians never stops to surprise me. Okay, so thanks a lot for everyone.